Have you ever gazed at the night sky and wondered, how did all of this come to be? How did the universe, with its countless stars, planets, and galaxies, emerge from nothing? A time when there was no time, no space, no matter. What sparked the creation of everything we know? Today, we're embarking on a thrilling journey to uncover the origins of our universe. From the explosive birth of the Big Bang to the mysterious realms of quantum fluctuations and the mind-bending possibilities of the multiverse, get ready to explore the most profound question of all. How did everything start from nothing? Buckle up, because this cosmic adventure is about to begin. Welcome to the most intriguing journey of all time, understanding the origin of everything from nothing. Our story begins about 13.8 billion years ago with a theory that has revolutionized our understanding of the cosmos, the Big Bang theory. Imagine everything in the universe, every atom, every star, every galaxy, compressed into a single point of infinite density and temperature. This point is what scientists call a singularity. At this singularity, the laws of physics as we know them break down. There is no space, no time, just an incredibly hot and dense state. And then it happened. In a fraction of a second, this singularity began to expand. This event wasn't an explosion in space, it was an expansion of space itself. Think of it like a balloon being inflated, with galaxies, stars, and planets being carried along the surface as it stretches. This is the essence of the Big Bang, a rapid expansion that set the universe into motion. As the universe expanded, it cooled. This cooling allowed energy to convert into various forms of matter. Within the first few minutes, protons and neutrons combined to form the nuclei of the lightest elements, hydrogen and helium. This period is known as nucleosynthesis. However, it wasn't until about 380,000 years later that the universe cooled enough for electrons to combine with these nuclei, forming the first stable atoms. This era is known as recombination, and it marks the moment the universe became transparent to light. Evidence of this early stage of the universe is still visible today in the form of the cosmic microwave background, CMB radiation. Discovered in 1965 by Arno Penzias and Robert Wilson, this faint glow permeates the entire universe and provides a snapshot of the infant universe just after recombination. The CMB is a critical piece of evidence supporting the Big Bang theory, giving us a direct view of the universe when it was just 380,000 years old. But what happened after the universe became transparent? Gravity began to play a crucial role in shaping the cosmos. Small fluctuations in the density of matter led to the formation of massive clouds of gas. Over hundreds of millions of years, these gas clouds collapsed under their own gravity to form the first stars. These first-generation stars were massive and short-lived, ending their lives in violent supernova explosions. These explosions scattered heavier elements like carbon, oxygen, and iron into space, enriching the cosmic gas with the building blocks necessary for the formation of planets and eventually life. These heavier elements, now mixed with hydrogen and helium, clumped together under the force of gravity to form new stars and planetary systems. This cycle of star birth and death has continued for billions of years, creating the complex and dynamic universe we observe today. Galaxies, the grand structures of the universe, began to form as gravity pulled together vast collections of stars. Over time, these galaxies evolved, merging with others and growing larger and more complex. Today, we see a diverse array of galaxies, spirals, ellipticals, and irregulars, each with its own history and population of stars, planets, and perhaps even life. The Big Bang theory not only explains the origin of the universe, but also provides a framework for understanding its evolution. From the initial singularity to the formation of atoms, stars, and galaxies, this theory offers a comprehensive narrative of how everything we see today came to be. But our journey doesn't end here. As we delve deeper into the origins of the cosmos, we uncover more mysteries and questions. Stay with us as we continue to explore how everything started from nothing. Formation of stars and galaxies. As the universe continued to expand and cool, the smooth sea of hydrogen and helium gas that filled space began to clump together under the force of gravity. These clumps, initially small and relatively uniform, started to form denser regions known as dark matter halos. Dark matter, though invisible, played a crucial role in the formation of structure in the universe by providing the gravitational scaffolding necessary for ordinary matter to gather and form galaxies. Within these dark matter halos, hydrogen and helium gas continued to collapse and cool, leading to the formation of the first stars. These stars, known as population 3 stars, were massive and short-lived. Unlike stars today, which contain heavier elements, these early stars were composed almost entirely of hydrogen and helium. Their immense mass meant they burned through their fuel quickly, ending their lives in powerful supernova explosions. When these first stars explode as supernovae, they scattered heavier elements, such as carbon, oxygen, and iron, into the surrounding space. This process, known as nucleosynthesis, was crucial for enriching the interstellar medium with the elements necessary for the formation of planets and, ultimately, life. These supernovae also triggered further star formation by compressing nearby gas clouds, leading to the next generation of stars. As time went on, these regions of star formation grew larger and more complex, forming the first proto-galaxies. Gravity continued to pull these proto-galaxies together, merging them into larger structures. Over billions of years, these mergers and interactions led to the formation of the diverse array of galaxies we see today. Spiral galaxies, like our Milky Way, elliptical galaxies, and irregular galaxies. Galaxies are not just random collections of stars, they are dynamic systems with intricate structures. For example, spiral galaxies have distinct arms that wind outward from a central bulge, where a supermassive black hole often resides. These arms are regions of active star formation, glowing with the light of young, hot stars. Elliptical galaxies, on the other hand, are more rounded and contain older, cooler stars with less star formation activity. Within these galaxies, stars continued to form and evolve. Around many stars, particularly those in stable regions of galaxies, disks of gas and dust formed. These protoplanetary disks are the birthplaces of planets. Dust and gas within the disks clumped together to form planetesimals, which collided and merged to create planets, moons, asteroids, and comets. This process of planetary formation is incredibly complex and can take millions of years. Some regions within the disk might form rocky planets like Earth, while others might form gas giants like Jupiter. The diversity of planets and their compositions is a direct result of the conditions within the protoplanetary disk and the star's properties. Today, we know of thousands of exoplanets orbiting other stars, thanks to missions like NASA's Kepler and TESS. These discoveries have shown us that planets are common in the universe, and they come in an astonishing variety of sizes and types. From rocky super-Earths to gas giants larger than Jupiter, the potential for diverse planetary systems is vast. The formation of stars and galaxies is a testament to the dynamic and ever-changing nature of the universe. From the ashes of the first stars to the birth of complex galaxies, This cosmic dance has been ongoing for billions of years, shaping the universe we inhabit today. But the story of how everything started from nothing doesn't end here. There's still more to uncover about the deeper mechanisms at play, including the role of quantum fluctuations and the possibility of a multiverse. Stay with us as we continue this fascinating journey into the origins of everything. The role of quantum fluctuations. But what about before the Big Bang? How did that initial singularity come into existence? Here's where things get really fascinating and where the mysterious world of quantum mechanics comes into play. Quantum mechanics describes the behavior of particles at the smallest scales, where the rules of classical physics no longer apply. According to quantum mechanics, even in a perfect vacuum, seemingly empty space, there are constant, tiny fluctuations in energy. These fluctuations give rise to pairs of particles and antiparticles that appear and annihilate almost instantaneously. This phenomenon is known as quantum fluctuations. Think of it as a sort of cosmic dance at the smallest scales, where particles pop in and out of existence. Now imagine if one of these tiny fluctuations didn't disappear. Instead, it began to expand rapidly, driven by an enormous amount of energy. This is where the concept of inflation comes into play. Proposed by physicist Alan Guth in the early 1980s, inflation theory suggests that a fraction of a second after the Big Bang, the universe underwent an exponential expansion, growing from subatomic scales to macroscopic ones in an incredibly short time. During inflation, the energy from the quantum fluctuation was converted into a hot, dense plasma, which then continued to expand and cool, leading to the formation of the universe as we know it. This inflationary period explains why the universe appears so uniform on large scales, solving several key problems in cosmology, such as the horizon and flatness problems. Quantum cosmology posits that our universe could have originated from a minuscule quantum fluctuation in a higher dimensional space, potentially spawning numerous other universes with diverse physical laws, a hypothesis known as the multiverse theory. This concept challenges our understanding of reality and raises profound questions about existence. Ongoing research, such as experiments at the Large Hadron Collider, seeks to simulate conditions akin to the Big Bang, offering insights into our universe's origins. Exploring these mysteries not only deepens our cosmic knowledge, but also prompts us to reconsider our place within a potentially vast multiverse, pushing the boundaries of our comprehension of existence itself. The multiverse theory. The multiverse theory proposes that our universe is just one among myriad bubbles within a vast cosmic foam. Each bubble represents a distinct universe with unique characteristics, potentially governed by different physical laws and dimensional properties. This concept draws from string theory, where fundamental particles are envisioned as vibrating strings in a higher dimensional space, allowing for the emergence of diverse universes. Cosmic inflation theory suggests that during the universe's rapid expansion, pockets of space could have ceased inflation at different times, giving rise to separate universes with varying conditions. Quantum mechanics contributes to the multiverse theory through the idea of quantum decoherence, which posits that every quantum event creates a branching of realities, each unfolding into its own parallel universe. This notion challenges our conventional understanding of reality by proposing an infinite array of parallel universes where physical constants, gravitational forces, temporal flow, and even the existence of life forms can differ radically. The multiverse theory thus opens up a profound exploration into the potential diversity and complexity of cosmic existence beyond our observable universe. While the multiverse theory is captivating, it remains highly speculative. Scientists are actively seeking ways to test and validate these ideas. For instance, researchers look for subtle imprints in the cosmic microwave background radiation that could suggest interactions with other universes. High-energy particle experiments, like those conducted at the Large Hadron Collider, also explore the fundamental properties of particles and forces that might provide clues about the existence of other dimensions. The multiverse theory pushes the boundaries of our understanding and raises profound questions about the nature of reality and our place within it. If our universe is just one of many, what does that mean for our understanding of existence? Are there other versions of ourselves living different lives in parallel realities? What are your thoughts on this? Let us know in the comments down below. If you find our video informative, then like it and share with your fellow space enthusiasts. Subscribe to our channel for more content space science, and don't forget to hit the bell icon to never miss an update from us.